In this video, we will discuss the Van Hoff factor. We have already seen the Van Hoff factor, here represented by the italicized I, in boiling point elevation and freezing point depression, but also occurs in osmotic pressure of a solution. So what is it? Well, colligative properties, what we're talking about here, are properties that depend on not the concentration of a compound, but on the absolute number of solute particles in solution. What does that mean? Well, for example, if we take 1 mole of sucrose and dissolve it in water, well, we get 1 mole of dissolved particles. However, if we take 1 mole of sodium chloride, an electrolyte, we actually get 2 moles of particles, in this case ions. And if we take 1 mole of sodium sulfate, we get 3 moles of particles. So, the Van Hoff factor for sucrose is just 1, Van Hoff factor for sodium chloride is 2, and for sodium sulfate it is 3. In theory. Turns out, as you have higher concentrations and with certain ions, you get what's known as ion pairs. So for instance, we take a look at our sucrose again. We would normally calculate that it has a Van Hoff factor of 1, and it turns out, yeah, at 0.05 molar, it has a Van Hoff factor of 1. We take something like hydrogen chloride. It's ionic, it's going to split into hydrogen and chloride ions, and we would expect a Van Hoff factor of 2. Turns out that because you don't get complete dissociation, you get some of these ions, they seem to repair up a little bit. You actually have a measured Van Hoff factor of 1.9. And then if we take a look at iron 3 chloride, which we would expect 4 particles dissolved for every 1 mole of compound, well, we actually get a Van Hoff factor of 3.4. So depending on what size you have of ions and concentration, you're going to have a slightly less Van Hoff factor in reality than what you've calculated. And when it comes to concentration, this graph shows it off pretty well. It drops off real fast for high concentration solutions. But that's just in theory. We're only really interested in what it is calculated. So if we see an electrolyte, we just count how many ions are present in that electrolyte, and that'll give us our theoretical Van Hoff factor. However, we can use something such as osmotic pressure to determine what the actual Van Hoff factor is. Now, osmotic pressure is just the drive to dilute a solution as compared to a pure solvent. So if you have a semi-permeable membrane between a pure solvent and a solution, well, you're going to have some drive to dilute that solution there on the right. And this can actually be measured, and it is completely dependent on, well, this time molarity, and our gas constant and our temperature. Now in this case we're using our old style gas constant that relates liter atmospheres per Kelvin mole, and it also involves the Van Hoff factor, because this is completely dependent on the number of particulates. So how do we use this? Well, let's say we have a solution of potassium iodide. We would expect that to have a Van Hoff factor of 2, but we make a solution and we measure the osmotic pressure at 25 degrees Celsius, and we get an osmotic pressure of 0.560 atmospheres. We're going to use this information to determine the experimental value of the Van Hoff factor for Ki at this concentration. And so we're going to need to know the conversion factor for Celsius to Kelvin, as well as the gas constant. First, find out the concentration of our solution. So we take our moles of Ki per liter of solution. We go ahead and convert our temperature to Kelvin. And then we rearrange our equation to determine what I is. Again, we're expecting a Van Hoff factor of around 2. So we're going to plug in our given atmospheric pressure, our given osmotic pressure, divide that by the molality, divide by the gas constant, divide by the temperature in Kelvin, and it turns out that at this concentration, which is a fairly high concentration, we actually have a Van Hoff factor of only 1.79, as compared to the expected 2.